Okay, welcome to lecture here. We're continuing on talking about Lewis structures and bonding, all that good stuff. Good. A couple things. Okay, so we're continuing on talking about bonding. A reminder, as I mentioned last time, we will we'll have lecture like normal, and the quiz that we're going to take will be open at the start of lab. So at 7:15, right around there, it will open. You could take it at that point, and we'll talk more about that towards the end here at lecture. But you'll take the quiz, and then after the quiz, we'll meet up. We'll talk about the experiment and all that good stuff, and that'll be the rest of the day happening. Okay, so we got into bonding last time. We got into talking about different types of bonding. We talked about ionic bonding. And remember that with ionic bonding, that is when we have a metal and a non-metal that comes together. And always when you have a metal and non-metal that come together, it pretty much will make an ionic bond. And really what that means is what we have is no sharing of electrons, but we have a transfer of electrons from the metal to the non-metal. So the metal will lose the electrons, non-metal will pick up the electrons. The metal will become positively charged in a cation. The non-metal will become negatively charged and become an anion, and it is that electrostatic attraction between the positive and the negative guy that holds that together in an ionic bond. Again, absolutely no sharing of electrons happening in that situation. Now, the purpose of that sort of bonding, and really all bonding, is what happens in that case is when the metal does lose those electrons, it backs up to the noble gas that comes right before it in terms of its electron configuration and ends up with the same electron configuration as the noble gas. And the nonmetal, when it picks up those electrons, it actually is able to move forward to the noble gas that comes after it on the periodic table. And again, they both are able to achieve that noble gas configuration. And that really is the purpose of all bonding, is for everybody to be, as we talked about, was referred to as being isoelectronic with a noble gas. Isoelectronic basically just means that it has the same electron configuration. So everybody tries to get to that same electron configuration. When we do that, and when we're drawing those using Lewis dot symbols or Lewis or electron dot symbols, we do use the symbol and one dot to represent each of the valence electrons. The valence electrons, again, being the highest energy electrons, the ones furthest from the nucleus, and the ones that are involved in bonding. And the easy way to figure that out, other than writing the electron configuration, is the number of valence electrons equals the group number. So whatever group that element is in will be how many valence electrons it has, and that's basically what it will sort of transfer. And we then started talking about covalent bonding, and covalent bonding is a little bit different than that. Covalent bonding is when we get two nonmetals together. So as we talked about with all those sort of periodic trends, because they're two nonmetals, because they're hanging out pretty much in the same spot on the periodic table, the upper right-hand side, they share very similar properties in terms of electronegativity, ionization energy, electron affinity, size, and all those type of properties. And what ends up happening when two nonmetals pretty much hook up is that they end up deciding we will share electrons rather than transfer electrons. So the sharing of electrons can be equal sharing, or it may be unequal sharing. And what helps us decide that is what we talked about last time as well, which is electronegativity. So electronegativity really helps us sort of decide whether or not those electrons will be shared equally. So last time we saw an electronegativity table, I believe, and it runs from 0 to 4, 4 being the most electronegative. And essentially what you do is you take the two atoms that are involved in the bond and you subtract electronegativity values. And if somewhere between 0 to 0.4 the difference, is considered a nonpolar covalent bond. And what that essentially means is that we sort of anticipate those electrons are going to be shared equally. So a difference of 0 is like perfect equal sharing. Somewhere up to 0.4 is still considered equal sharing, even though there is a slight difference, but it's still considered equal sharing. And that's what's referred to as a nonpolar bond. If we do the difference in electronegativity between the two atoms and we get something like 0.5 below 2 as the difference in those electronegativity values, that is some type of polar covalent bond. And a polar covalent bond is one where we have unequal sharing of those electrons, and they will go towards, the electrons will head towards the more electronegative atom. And we can represent that one of two ways. We can use an arrow where it points to the more electronegative atom, or we can use sort of a partially positive, partially negative sort of symbol. And the reason that we have that partially positive and partially negative side is because, again, we have this unequal sharing. So as the electrons go towards one of the atoms in that bond, that side of the bond becomes more negative. And obviously, as the electrons move away from the other side of that bond, that side becomes more positive. And again, as we talked about last time, they are partially positive and partially negative because we have not had a full electron transfer. So they're still hanging on, but again, not hanging on equally. And again, that's what's referred to as a polar covalent bond. If we do that electronegativity difference and we really do get above 2, usually what that indicates is an ionic bond and we have no sharing of electrons. And as we talked about last time, don't really even need electronegativity values usually to identify an ionic bond, as long as you can identify it as a metal and a non-metal together, and that's pretty sufficient to do that. So we talked about different types of electrons as well. Just before we continue on here, remember that the electrons are represented like we see on the screen here as dots that are not involving in any type of bonding. Those are what are referred to as non-bonding electrons, are lone pairs. And then obviously the electrons that are involved in a bond between two atoms, those are what are referred to as bonding electrons. So when we draw Lewis structures, as we finished up on last time, you really do want to sort of follow the steps that we talked about. Again, that will typically lead you to a pretty good structure when it's all said and done. Again, you don't want to kind of do piecework where you take every individual one and kind of try to figure out how to put them together. So a couple important steps along the way that we talked about. First off, you want sort of a logical sort of arrangement of all the atoms together to help you make that decision. Usually the least electronegative atom is found in the center. And most of the time, everybody else is attached to that center guy. Not 100% of the time, but a lot of times everybody's sort of attached to it. We never find fluorine or hydrogen in the center, and that is because fluorine is the most electronegative atom, and hydrogen cannot be in the center. It can only be on the outside because out of all the elements, hydrogen is pretty much the only one that should not have 8. It should only have 2 electrons, which means it does need to end up on the outside. It can never find itself on the inside. Otherwise, it will end up with too many electrons. So once you have sort of the logical arrangement, the next really important thing to do is to make sure that you know the total number of valence electrons. So you want to count up the total number of valence electrons. That includes if a thing does have a charge. If it has a negative charge, you need to add to your total of electrons. As a positive charge, it means it lost electrons, so you need to get rid of electrons from your total. And that number is really important because when your picture is done, you need to have exactly that number of electrons on your picture, no more, no less, in order for you to have the correct picture. Once you've done that, you want to make a single bond to the center guy to all the outside atoms. You want to figure out how many electrons you've used up. And then any leftover electrons go on the outside atoms in pairs, dots, until all the outside atoms have 8, unless obviously it's hydrogen, so no dots on those. And if you fill up all the outside atoms with 8 and you still have electrons, then you go to the center atom, and that's where you would put electrons on as pairs as well as dots on the center atom. At that point, you probably have used up all your electrons, which means what's left to do is to make sure everybody has met the octet rule. And if somebody has not met the octet rule, it is at that point where you do want to fix it by making a double bond or a triple bond. Double bond to sort of fix it, triple bond if the double bonds sort of don't fix it. As we talked about last time, you usually don't want to just double bond and triple bond right out of the box. You kind of want to save it to kind of fix things is usually what you do. Any questions on that stuff there that we talked about last time? Okay, so we did this example here kind of following that process again. we counted up our total electrons, nitrogen in the middle. We started with one line out to everybody. That was 6 electrons. We filled up the outside ones in pairs till they were all filled up. We had 2 left over at the end, which we did place there on the center at the end. And we had a grand total here, 26 electrons. And if we count up everybody, everybody has 8 electrons, so they're perfectly happy. All right, so let's try another one here. So you have that one. Try CO3 2 minus and see what you come up with. And again, if you have a periodic table, it probably will be helpful here for you. So take a moment or two here and draw it up. Okay, so let's take a look and sort of see how to approach this. So one of the first things you can do is count up the total number of valence electrons. So we got carbon, which is group 4, which means it has 4 valence electrons. There's 3 oxygens, each at group 6, which would be 6. We do have a -2 going on here. So minus means that it gained electrons. 2 is how many electrons? So we do want to make sure we add those 2 in. And that's 18, 20, 24 electrons. Looks good. So we pretty much have 1 carbon and 3 oxygens. So carbon would go in the middle. Also, if you look on the periodic table, carbon is further to the left, which means it should be less electronegative, again, without even the need of the numbers. So carbon in the middle, some oxygens there around. Again, you could put the oxygen on the bottom if you want, or the top. We're going to do a single covalent bond to everybody, and that is now going to use 2, 4, 6 electrons. We do have some more to go and go with 18 perhaps is left there. We're going to put those on as pairs on the outside. So 2, 4, 6, that's going to fill that guy up. 8, 10, 12, that's going to fill that guy up. 14, 16, and 18. That's going to fill that one up. At this point, if we count up the total number of electrons that we have placed up here, it is 24, which is good. Oxygen on the right here has 2, 4, 6, 8 electrons. All the oxygens are exactly the same, so they all have 8. The carbon, though, in the center has 2, 4, 6 electrons. So it is actually short. So it does not meet the octet rule. So this is the situation where we do want to try to fix it to get everybody to 8. So sometimes people ask, can I just do this and put up a couple of electrons there? And that would give carbon 8 electrons. But the problem with that is we now will have 26 electrons, and that's not good. So again, you cannot just put some more electrons on the picture. Otherwise, you will end up with too many electrons. So this is the part where we actually do want to make a double bond to fix it. At this point, we have 3 oxygens. They're all pretty much identical. You could double bond anywhere you like. So if I double bond here, that will fix the carbon. But again, we have the same problem. We're going to end up with 26 electrons if we just draw the line. So we can't just draw the line. We can't just put dots. We do have to make a double bond. But when we do make a double bond, what we're going to do is take a pair of electrons and basically bring them in to make the double bond. So I'm going to take the pair on top, and I'm just going to get rid of those up there on top, and also that 4 that was up there as well. And now we're going to bring those electrons in and make the double bond. And what this does by bringing those electrons in, putting some brackets around it to make it look pretty and all that good stuff there, we get this structure here, which now if we count it up, we have 2, 4, 6, 8 electrons on the oxygen on the left, 8 electrons on the oxygen on the right. The double bonded oxygen up on top has 2, 4, 6, 8 electrons, and the carbon now has 2, 4, 6, 8 electrons, and they all have 8 electrons. There's a total of 24 electrons, and usually when you have something with a charge, you put brackets around it and the charge on the outside to make it look nice. You absolutely could have double bonded any of the oxygens in this case. So you could have just laid up the double bond there on the left if you liked. We'll leave the top guy single bonded. That would have been perfectly fine as well. And you could have done the double bond there on the right. Perfectly okay as well if you drew it sort of like this, maybe neater than this. Let's see here. Yeah, I feel like I lost an electron there. And all 3 of these structures would be perfectly fine. All 3 of these structures are actually what are known as resonance structures. So these are what are sometimes referred to as resonance structures. And sometimes we'll use this 2-headed arrow between the structures. And basically what they are known as resonance structures because in this case, we did have that option as to where we could make that double bond, and you could have double bonded in any of these sort of places. The true structure is actually somewhere between all 3 of these, and that's because those double bond electrons are sometimes what is referred to as being delocalized, which means they're kind of moving around. So at any given point in time, they may be over here at this oxygen, or they may then kind of travel over here to this oxygen, may travel over here to this oxygen. So we draw resonance structures really when one structure doesn't really adequately sort of describe what the true structure is, and really the true structure is probably somewhere between all 3 of these. So you could have drew any one of those 3, so it would have been perfectly fine. If it didn't ask you to draw a resonance structure, you could lay up any one of those 3 pictures and it would have been okay. Any questions on that particular one there? Okay. So I think got another one maybe, or not. Like I skipped one somewhere. All right, so let's do just a couple more here. Why don't you draw these Lewis structures and see what you come up with. Why don't you do, let's do SO2. Why don't you do N2? Why don't you do HClO4? And let's go with H2S. So why don't you take a couple of minutes here and draw the Lewis structures for these guys to see what you come up with. I'll give you a hint on this one here. One of the hydrogens connected to one of the oxygens, chlorine in the middle. So chlorine in the middle, oxygens around, and like one of the hydrogens connected over there. So sort of that deal. Okay, so let's see how we're doing here. We'll start with the top one. So we will count up the total number of valence electrons here. So sulfur is group 6. There's 2 oxygens, which are also group 6. That is 18 valence electrons here. In this case, sulfur will go in the middle, oxygen on the sides, sulfur being least electronegative here. And we're going to do a single bond from the center to the outside. That's 4 electrons. That gives us 14 more to go. So we're going to fill up the outside in pairs. So that's 2, 4, 6, 2, 4, 6. I'll learn to count. 8, 10, and 12. At this point, we have now placed up here 16 electrons. We actually still have 2 more to go. Always missed on this one is those 2 will actually go right there on the center atom in pairs. And again, by placing those electrons that way, that is how we actually do get those pairs there. Can't tell you how many times I've seen this drawn with nothing there on that S. We have now used all 18 electrons. We want to make sure that everything has met the octet rule. Oxygens on the left and right actually have 8 if you count around, so 2, 4, 6, 8. Sulfur, though, in the middle only has 6, so that's not so good for sulfur. So this is another case where we do need to make a double bond. Just like the last one, in this particular case, we could double bond on either of the oxygens. So I'm going to do the guy on the left here first. So I'm going to take away a pair of electrons there. I'm going to bring that pair of electrons in to make my double bond, and we will end up with something that looks like this. The guy on the left now has 2, 4, 6, 8 electrons. Oxygen on the right, also 8 electrons. Sulfur now has 2, 4, 6, 8 electrons. So this is the proper structure for SO2. And again, by placing those electrons in the proper order, that is how we get those dots on there. This one as well, you could draw a resonance structure, which is just the double bond on the other side, if you wanted to do it that way. And again, either one would have been a perfectly fine structure. Any questions on that particular one there? Let us go down here to, this is perchloric acid actually. So hydrogen is 1 electron, chlorine is 7, and there's 4 times 6 for the oxygens. That's a lot of math there. That's 24 and 7, and it's like 31, maybe a 32 if I counted right there, hopefully. Again, this is a logical arrangement for this, and you might not know this, but this is an acid, and pretty much acids have this O and H bond. That's pretty much what makes them an acid. So we're going to follow the same sort of approach here. We're still just going to make a single bond to everybody. And at this point, by making the single bond to everybody, we've now used 2, 4, 6, 8, 10 electrons. That leaves us 22 more to go. We're going to do the same thing as the others. We're going to work outside in. Hydrogen cannot take any more electrons. It is full at this point. So we then will go to the oxygens. That's going to be 2, 4, 6, 8, 10, 12, 14, 16, and 18. At this point, I have now put on there 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28 electrons. My math there tells me I got 4 more to go. Next outside one is the oxygen, and it would get a pair of electrons there, which gives it 6, and another pair there, which gives it 8. I have now, if I have not made a mistake here, placed 32 electrons on this. We want to make sure that everybody's good. So oxygens all have 8, 2, 4, 6, 8. The oxygen with the OH group here has 8 around it, 2, 4, 6, 8. Chlorine has 2, 4, 6, 8. And hydrogen has just 2, which is exactly what hydrogen needs in this case. And again, this part of it, as you'll learn later on, that is pretty much what makes it an acid. That's the H that basically pops off to make it an acid. Any questions on that particular one there? Okay, so rolling to N2, That is 2 times 5. That is 10. So nitrogen and nitrogen, no real center atom here. We're going to do the same steps so you can kind of see how we get to the right structure here. Single bond takes 2 away, leaves us 8. We're going to put those on the outside in pairs. So that guy is full. We now have 2 more to go, which we'll put here. And at this point, nitrogen on the right is okay. It's got 8. Nitrogen on the left, not so good. It has got only 4 electrons. So at this point, we want to make a double bond to fix it. So just like before, I'm going to take a pair of electrons out. I'm going to put a double bond in. And when I put a double bond there, I now have 2, 4, 6, 8 for the nitrogen on the right. On the left is better, 2, 4, 6, close, but not there. So this is the point where now I've pretty much exhausted all my double bond possibility. I need to make a triple bond in this case. And we do the same thing. We need to take a pair of electrons out and bring them in. And when I do that, I'm going to bring those electrons in, and that is going to give me my triple bond that we associate here with nitrogen. Again, now this is going to give both nitrogens left and right 8 electrons. Question on that particular one there. And lastly here, 2 times 1 for our hydrogen, and 6 there, that is 8. So we're going to go sulfur in the middle. Again, hydrogen cannot be in the middle. Same approach, 1 single bond to everybody. Going to leave us now 4 more electrons. Hydrogen's full on the outside, hydrogen's full on the outside. So at this point, we are going to go with dots here on the central atom, and that will give us the 8 electrons on the sulfur and 2 electrons each on the hydrogen, which is exactly what we need here. Any questions on how to draw Lewis structures? Again, you do want to kind of follow these steps, single bond everybody, distribute those electrons in pairs until you've distributed them all, and then go with the double bond or triple bond at the end if you need to fix something. And like I said, usually that'll give you a pretty good picture. Maybe not the best picture, but it'll usually give you the closer to right picture, I would say. Other than that, when people really start trying to double bond or triple bond out of the box, like I said, they usually will end up with not the right lone pairs, too many bonds, and those type of things. Any questions on any of that? Okay. All right. So let us continue then. Here we go. All right, so let's talk a little bit about formal charge in Lewis structures. So one way, you know, if you've driven something, but maybe if you've also drawn something as well. If you've drawn some Lewis structures before, you know, you might have had a situation where you're like, I think I could draw it a different way, or maybe I could draw it another way. And you may be able to even count up all the electrons, and all the electrons will be perfect in terms of the right amount and all those type of things. And one thing that sort of helps us determine what might be a better Lewis structure than another is something known as formal charge. And formal charge is the difference between basically the valence electrons in the free atom and really sort of the number of electrons that is in the Lewis structure that you assign. So to calculate the formal charge, and you can calculate the formal charge on every element in a particular picture, the formal charge is equal to the total number of valence electrons in the free atom. So just like you would count it from the periodic table, minus the total number of non-bonding electrons. So those are the dots in your picture, minus 1/2 the number of bonding electrons. So those are the lines in your picture. So lines represent 2 electrons. So you could use this to really determine sort of the charge, if you will, on everybody. So total number of valence electrons minus number of non-bonding electrons minus 1/2 the number of bonding electrons. So for example, here, if we look at ozone, and if we draw ozone, again, O3, That is 3 times 6, which is 18. And if we do that, you can't mess this up. It's all oxygens here. So we're going to do a bond to everybody. We're going to go 2, 4, 6, 8, 10, 12, 14, 16, and we will have 2 more here. It will be 18. We are going to need to make a double bond here because the oxygen in the middle is not so right. So we can double bond over here. And we do need to get rid of a pair of electrons there. We'll get rid of those right there. So this would be our structure here for ozone. We could also draw a resonance structure for this as well, double bond on the right-hand side. We could calculate the formal charge on everybody that's here. So why don't we take a look at the single bonded oxygen, which looks something like this. And if we were to calculate the formal charge on this guy, which would be number 1 over here, it would be number of valence electrons in oxygen, which is 6, number of non-bonding electrons, and again, individual, so 2, 4, 6 dots, minus 1/2 the number of bonding electrons, which is this guy here, and that represents 2 electrons. So that is 6 minus 6, that's 0, minus 1/2 of 2 is 1. So that is a -1 would be the formal charge over here on that particular oxygen. If we do the guy in the middle, the guy in the middle kind of looks like this. And that is 6 for the number of valence electrons in oxygen, minus there's only 2 non-bonding electrons, minus 1/2 the number of bonding, which is 2, 4, and 6. That is 6 minus 2, which is 4, minus 3. That is +1 here. And that would be the formal charge on that oxygen right there would be +1. And if we do our last oxygen over here, which is our double bonded oxygen, it would be 6 minus 4. Again, 4 dots there, minus 1/2 of our bonding, which is 2 and 4. And that would be 6 minus 4 is 2, minus 1/2 of 4, which is 0. So the formal charge here would be 0 on this particular guy. Now, when you add up the formal charge, if it's a sort of good structure, it should equal the overall charge of the molecule. So since ozone is neutral, +1 minus 1 is 0. So that's all good on calculate the formal charge here. Okay, let's see here. I think maybe do we have... So why don't you do it for carbonate? So why don't you take a couple of seconds here, minutes, and calculate the formal charge on each of the elements there in, or each of the bonds, basically atoms there in carbonate. So what's the formal charge on the carbon and the 3 oxygens? So take a minute or 2 and calculate that, and we'll talk about it. Okay, so let's take a look. So we'll take each of these elements separately. So we'll start with the single bonded oxygen, and we have one on each side. So again, looks something like this. So we're going to go with 6 for the number of valence electrons in oxygen, minus 6 here because there are 6 non-bonding electrons, the dots, minus 1/2 the number of bonding, which would be 2 for the line. And that is going to give us 6 minus 6 minus 1, gives us a minus 1. So the formal charge on the oxygen on the right there is minus 1. And since the one on the left is identical, it will also be minus 1 in terms of its formal charge. We do the double bonded oxygen there on top, looks something like this. Again, 6 minus 4 for our non-bonding electrons, minus 1/2. We got 2 lines, so that's also going to be 4. So that's 6 minus 4, which is 2, minus 1/2 of 4, which is 2. That is 0. So the formal charge of this guy here is going to be 0. And our carbon there in the center looks something like this. Carbon has 4 valence electrons, minus 0 for non-bonding, so there's no dots. Minus 1/2, there is 2, 4, 6, and 8 bonding electrons. And that's going to give me 4 minus 4, which is 0. So these are the formal charges here in this particular ion. And we can see that overall, this guy has a minus 2 charge. And the minus 2 charge is really from the oxygen on the right and the oxygen on the left in this picture. Minus 1 and minus 1 gives us our minus 2 charge that we associate with carbonate based on how really the electrons are being shared in the bonding that happens with carbonate. So that's why we actually kind of get that minus 2 sort of overall charge is where that comes from. Question on how to calculate the formal charge. So one aspect of formal charge is you could literally kind of do this and really calculate the formal charge of each of the individual elements that are present. What we oftentimes will use formal charge, like I was sort of talking about just a second ago, is we will oftentimes use it to help us decide maybe between a couple of different Lewis structures that we may draw. So again, as I mentioned, for a lot of pictures or Lewis structures that you draw, you technically can come across several different sort of connectivities of the elements and bonds, double bonds, triple bonds, single bonds. And it may be fine in terms of numbers of electrons and everybody meets the octet rule. But there is a way you could kind of determine if maybe one Lewis structure is maybe better than another, and formal charge is oftentimes used to do that. So some general sort of rules for formal charge is this: if you have a neutral molecule, a no formal charge is sort of preferred. So if you could get everybody to end up with in a picture pretty much formal charges of zeros, that's probably your best picture that you can make. Usually if you draw a Lewis structure and you calculate the formal charge and you have really large formal charges like 2s and 3s, probably not the best picture in terms of the arrangement of all those guys. And lastly, if you sort of have a choice for sort of the distribution of charge, you want in a Lewis structure the more electronegative element to have the more negative formal charge. So you could use some of these sort of rules here to help you choose between two pictures as to which one would be perhaps a better picture. So let's take a look at sort of how to do that. So if we had something like CH2O, which is formaldehyde, and you could come up with a couple of different sort of arrangements of formaldehyde if you were to draw it. And here are two possible ones. Let's just go through these two. If we go through all the steps that we just did, we can end up with these two pictures here, perhaps. And they both technically meet the octet rule for everybody. We've used the same number of electrons. This is a possibility that both of them could be good structures, maybe. So we can use formal charts to really help us decide which one would be a better structure. So let us start with the guy on the left here. If we do our hydrogen, Hydrogen is one valence electron minus no non-bonding electrons, minus 1/2 of 2, and that's going to give us 0. So the formal charge on this hydrogen is 0. Formal charge on that hydrogen is 0. If we do the carbon that is present, looks something like this. And that would give us 4 for carbon, minus 2 for the non-bonding electrons, minus 1/2 of 2, 4, and 6 electrons there. And that gives us 4 minus 2, which is 2, minus 3. So that's going to be minus 1 if my math is not too bad there. So that's going to give us a -1 formal charge there on the carbon. And our oxygen that's in that guy will look something like this. And that would be 6 minus 2 for the non-bonding electrons, minus 1/2 of 6. Again, 2, 4, and 6. That's going to be 4 minus 3, going to give me +1. So this is the formal charge arrangement for us connecting this guy in this fashion. So let's do the formal charge for the one on the right. So for the one on the right here, we have our hydrogen, which is going to come out the same. If you haven't noticed, they do come out the same once you figure it out. 1 minus 0 minus 1/2 of 2, which is going to give us 0. So hydrogen here is going to be 0. Hydrogen here is going to be 0. Double bonded oxygen looks like this, like we saw before. That's going to be 6 minus 4 minus 1/2 of 2, 4 for the bonding. It's going to be 6 minus 4, which is 2, minus 1/2 of 4, which is also 2. That is going to give us a 0 for this one. And lastly, our carbon in the guy on the right looks something like this. Going to be 4 minus 0 minus 1/2 of 8 for the bonding, 2, 4, 6, and 8. And that will give us a 0 there. So although we could draw two perfectly good looking, I guess, pictures, if you will, for this guy, depending on how we put it together, based on formal charge, hopefully you could decide the right one. Let me put a box around it just in case. It is the guy on the right would be the correct one here. I won't say the correct one, but it would definitely be a much better Lewis structure based on formal charge, because as we can see here, this is neutral, and pretty much we hit zeros on all of the formal charges, which makes it really good. Although this guy does have some zeros, not good because we do have some charges. Even worse here is the negative formal charge is on the carbon versus the oxygen, and the carbon is less electronegative than the oxygen. So remember that if we have sort of an even distribution of these formal charges, we would like the more negative formal charge to be on the more electronegative atom, which in this case would be oxygen. So that's another reason this is not the greatest of structures, and you probably would want to lay out that structure there as probably the best structure to draw as we hit all zeros. So this is a lot of times what we do use formal charge to help us decide between different structures as to what would be a better structure. Questions on that there? So I'm going to give you a couple to try here, and you tell me which ones are better structures. So let's say we drew carbon dioxide like this. And let's say everybody's favorite thing to do, I'm just going to lay up some triple bond because I like triple bonds. So we draw it like this. So you choose between these two and decide which one is the better Lewis structure based on formal charge. So calculate the formal charges and decide which one would be a better structure based on formal charge. Okay, so let us take a look. So starting here with the one on the left, we do our double bonded oxygen like we saw previously. That's going to be 6 minus 4 minus 1/2 of 4 for our bonding, which is here, 2 and 4. And that will give us 0 in terms of the formal charge. The one on the right will turn out the exact same way. The carbon in the middle looks something like this. So that's going to be 4 minus 0s. There's no dots. Minus 1/2 of our bonding, 2, 4, 6, and 8. And that gives us 0 as well. So we got zeros all the way around there. On the right here, we have our single bonded oxygen, which looks something like this, which is 6 minus 6 for our non-bonding electrons, minus 1/2 of 2 for our bonding electrons. And that does give us -1 when it's all said and done for this guy. Triple bonded oxygen. Don't see too much of that. 6 minus 2 minus 1/2 of 6. It's a lot of math there. That 6 minus 2 is 4 minus 3. I'll go +1 on that. Grab a calculator one of these days. And lastly here, our carbon going to look something like this. And that is going to be 4 minus 0. So there's no dots. Minus 1/2 of 8. And that will be 0 here. So hopefully you have decided that it is this one here. That is the better structure. Again, we hit 0 all the way across there, so that's pretty good. And here we do have equal distribution of the ones, but again, much better all zeros. So really formal charge can definitely be used to help us decide between sort of two competing Lewis structures. Are in some cases, should I connect this atom to this guy or put it over here and connect it to another one? You can draw the two structures. You could calculate the formal charge and you can again use sort of it to guide you towards the better Lewis structure. Any questions on formal charges or how to use it to calculate or help you decide? Any questions on any of that? Okay. So we talked a little bit about resonance structures, and again, resonance structures when you can move the double bond around to different locations, as we talked about. Essentially, that is when you can draw more than one Lewis structure, and it's because those double bond electrons are really moving around. But here we're going to talk a little bit first off, though, about bond length and sort of bond strength. You do not have to memorize this chart or anything like this, but if we look at this chart, we do see some patterns sort of develop. If we look here at the carbon-carbon bond, this is our single bond. That's our double bond, and that's our triple bond. And what we see in terms of the length, and this is the length between sort of nucleus to nucleus, we go from 154 to 133 to 120. So we also, if we look at our single, double, and triple bond here for the carbon-nitrogen bond, we go from 143, 138, and 116. So what we see is the distance between the two atoms does start to shrink as we keep putting on an extra bond. So as you can see here, single bond is longer than a double bond is longer than a triple bond. And what happens is kind of like what we were just doing, when we bring those electrons in to make those bonds, the electron cloud and everybody comes closer in, brings everybody tighter to each other, and the overall distance of everybody gets smaller and smaller. So single bond longer than a double, double longer than a triple. They're not like twice as long and 3 times as long, but that's sort of the general pattern that we see. And that does relate to bond strength. So in terms of bond strength, a triple bond is the strongest, a double bond is sort of the next, and a single bond is the weakest out of all of those. And that is because kind of like the brand new pencil type of example, take a brand new pencil out of the box, you could just take it and snap it. It's nice and long. If you take a couple of chemistry tests, you're down to like a nubbin and like an eraser, like really super small. If you try to break that, right, it's very hard to break. So it's the same idea here with sort of our bonds. As this length of it gets smaller and smaller, everything's held tighter, and it's much more energy to break a triple bond than, say, a single bond or a double bond. Same idea with that as well. It's not like twice the amount of energy needed to break a double bond or 3 times the amount of energy to break a triple bond, but that's the general sort of pattern that happens. And as we talked about it, electronegativity, which we did earlier, in case you fell asleep, I'm not sure why these are here again, but there's a nicer picture. We sort of did that, so we'll talk about bond polarity here, which we did as well earlier, but just a reminder, we can use electronegativity differences to help us distinguish between those types of bonds. And here's again a prettier picture, probably one I drew earlier the other day. These are our 3 examples. Remember that a pure covalent bond is really a nonpolar bond, and that's perfect equal sharing of electrons. So as you can see here, nice and equal sharing of electrons between the 2 chlorines. The difference here, 0.9 in our HCl, electrons heading towards the chlorine, being more negative on this side, more positive on the hydrogen, and our difference of 2.1, complete transfer of electrons from the sodium to the chlorine. All right. We talked about those, so we'll talk about that later, I think. All right, so let's talk though about bond energy, which is kind of what we were just talking about. So in terms of bond energy or bond enthalpy, we're going to talk a little bit about, how you could calculate the energy that's occurring when we sort of make bonds and break bonds. And when we actually break bonds, it's an endothermic process, which means heat and energy is absorbed. And what that basically means is if we have a bond that's together, it needs to absorb some energy. When it does, it has enough energy basically to wiggle away from each other. And on the opposite is true. If we have 2 guys wanting to come together, they're moving around a lot. They need to lose energy and kind of slow down and allow them to come together to make that bond. And when we do make bonds, it's an exothermic process where heat and energy is released. We talked a little bit about sort of endothermic and exothermic, and delta H, which is known as the enthalpy, is that heat of reaction. And when we calculate a delta H value that is positive, it is endothermic, which means overall that process absorbs energy. And if we calculate the delta H and it's negative, it's an exothermic process. And that means overall that process releases energy as a result of that. So one way that we can basically calculate what is sometimes referred to as the delta H of the reaction, or the enthalpy of the reaction, or the heat of the reaction, is basically to take the total amount of energy needed to break the bonds. That's essentially what happens when a chemical reaction occurs. So when a chemical reaction occurs, you basically need to break every single bond that's there. And we're going to add that to the total energy needed to make all the new bonds. And remembering, as we just saw there, since bonds being formed are exothermic, these guys are negative, and the bonds being broken or endothermic, these values are going to be positive. So really, when we're trying to figure out sort of the energy or the heat of a reaction based on bond energy, or bond enthalpy is sometimes referred to, it's kind of like an accounting sort of process. You need to figure out how many bonds you broke, what bonds you broke, how much energy it takes to break all those bonds. And secondly, you need to keep track of all the bonds that you made and how much energy it requires to make all those bonds. And depending on what type of bond is, single bond, double bond, or triple bond, you will have different values. And also what elements are involved. So usually when you do this type of calculation, what you want to make sure is that you actually know what everything looks like in terms of its Lewis structure. So sometimes it's very helpful to draw a Lewis structure of everything. That way you kind of physically kind of see the different bonds and keep track of them. Sometimes when people do it from the balanced equation, they either miss a bond or two, or they miss that, oh, that's not a single bond, that's like a double bond or a triple bond. So sometimes, it's really helpful if you're not sure what it looks like to kind of draw it and just kind of keep track of everything going on. And pretty much what's on this slide is what we just talked about. We're going to add up all the energy of the bonds broken and all the energy of the bonds made. So we have a table such as this, which obviously would be provided for you. This is from a different book, but a similar table is in your book. And this is what is known as the bond enthalpy table. And here's maybe a better picture so you can at least see it maybe bigger. And you could use these values here to basically add up everything that was broken, and then you want to add up everything that was made and pretty much add them together. So for example here, if we take a look at this, let's just keep track of what we did on this reaction. This is CH4 plus Cl2 goes to CH3Cl plus HCl. That's the reaction that's happening. So on the left-hand side, what has to happen is we need to break all these bonds that we see here. So if we keep track, we have 1 carbon-hydrogen bond, 2 carbon-hydrogen bonds, 3 carbon-hydrogen bonds, and 4 carbon-hydrogen bonds that need to be broken. So in terms of breaking, we need 4 carbon-hydrogen single bonds. You would go to that table and you would find the carbon-hydrogen single bond, which is right here, and it is 414 kilojoules. So that means that we would have 4 times 414 kilojoules. That is the energy required to break all 4 of those bonds. Now, when we come to the Cl2, we have 1 Cl2 bond that we need to break. So 1 Cl single bond. So we would go to our table and find the Cl single bond, which should be there somewhere there on the bottom. That's good. I'm going to go with 243. I think that's what it says. So 243. Now, that takes care of, in this particular reaction, every single bond that we are breaking on the reactant side. So if I grab a calculator, we got 4 times 414 plus 243. That is 1,899 kilojoules of energy is needed to be put in there to break all those bonds. And since breaking these bonds are endothermic, this value would be positive 1,899 kilojoules. First off, any questions on what we just did there? I see a question. Let's see. Yeah, so I think I understand what you're asking. You're probably asking, hey, we made 4 carbon-hydrogen bond, broke 4 carbon-hydrogen bonds on the left, and we actually are going to make 3 carbon-hydrogen bonds on the right. So 3 of those 4 cancel each other out, and they do. So you could do it that way, or you could kind of go individually through each one, so you don't miss anything. But in reality, it'll come out the same. So if that's sort of what you're asking, we're breaking 4 carbon-hydrogens, but also making 3 on the other side, so 3 of the 4 cancel. You can do it that way as well and just do a net of 1 carbon-hydrogen bond that's being broken. So we're going to go to the other side now, and we're going to see what we're making. So on the other side, in terms of making, we have 1 carbon-hydrogen, 2 carbon-hydrogens, 3 carbon-hydrogen bonds, which is what the question was just asking. So since we're actually making 3 carbon-hydrogen bonds here, that'll be also 414 kilojoules. But this is what I was just saying. The difference here is basically you broke 1. So you could have done just 1 and left the 3 off on this side, and it would come out the same. We also are making one carbon-chlorine bond over here. And if we look at the table there, carbon-chlorine is somewhere, carbon and chlorine, 339 it looks like there on the bottom, 339. And lastly, we are making one hydrogen-carbon bond, our chlorine bond, I'm sorry. And if we look at the hydrogen-chlorine bond, right there, 431 it looks like. So we got one at 400 and, see how old I am now? I just forgot that, 31, there it is. Hopefully I'll remember where I parked later. 431 kilojoules as well here. That takes care of everything that we have just made in terms of making. So if we do that, that is going to be, if my calculator will turn on, maybe, there we go, 3 times 414 plus 339 plus 431. That gives us 2,012 kilojoules of energy needed to make all of the bonds. Now, as we talked about, when you make bonds, it is exothermic, which means technically this number should be negative. And technically all these numbers here should be negative. Or you could just make the negative at the end. And to find the delta H for this reaction, all we need to simply do is add up both of those numbers. So positive 1899 kilojoules plus a negative 2012 kilojoules gives us 1899 minus 113 kilojoules of energy, which means based on this particular reaction and the making and breaking bonds or bond enthalpy, this is a exothermic process based on bond energy. Again, we know it's exothermic simply because it's a negative here, and that will tell us that it is exothermic. Question on that there. So this is sort of the simplest way to kind of do it. Just want to take each one. And again, if you're not sure what something looks like, you might want to draw it to make sure. So you have the right bonds, that there are single bonds, double bonds, or triple bonds. Any questions on that there? All right, so I think maybe we got one you could try yourself, maybe. That's the same one. That's good here. So why don't you try this one here and see what you come up with. And so that is H2O2. Let me go back this way. So the one that you have, I'll leave this up there so it might be easier for you to see. That was H2 plus O2, H2O2. And while you're at it, why don't you do this one as well? Why don't you do N2 plus H2 NH3. Do a 2 there and a 3 there. So once you do the delta H for each of those, I'll leave this one up, might be easier hopefully for you to see the numbers. Which again, if you're not sure, is a double bonded oxygen, which would be important in terms of picking the right one from the list. And then we had our hydrogen peroxide, which was something like this, I think. And if we look at what we're going to sort of break, we're going to break one hydrogen-hydrogen bond. And if we look at that on the list there, hydrogen is 436. So that's going to be 1 times 436. We're also going to break one oxygen-oxygen double bond, which is important when you go to the list. So again, you want to make sure that you grab the double bond value, not the single bond value. And that would be 498 in that particular case. And that takes care of everybody we're breaking. So that's going to give us 436 plus 498. Looks like 934 kilojoules. Again, this is going to be positive because we're breaking it, so it's endothermic. On the other side here, we are making a hydrogen-oxygen bond there and there. So that's going to be 2 hydrogen-oxygen single bonds. And again, if we go to our table here, that looks like 464 for that. So that's going to be 2 times 464. And the benefit of drawing this is a lot of people will forget all about this bond right here. You are also making a oxygen-oxygen single bond in the middle. So you got 1 oxygen-oxygen single bond. And again, by drawing it correctly, you'll know that is a single bond. And it looks like it is the 142 number, looks like there, that we're looking for. 142 kilojoules. There, if I got everything I think on that. So that's 2 and 2. So that is everything in terms of making. So that's going to be 2 times 464 plus a 142. That's going to give us a 1070 kilojoules. This is going to be negative since it is making exothermic. So delta H here would be 934 plus a negative 1070. And that would get us minus 136 kilojoules overall for this reaction. Also going to be exothermic in this case because it is negative. Questions on that particular one there? Okay. Let me go. I'll go maybe here. So the other one that we had was N2 plus H2 goes to NH3. So again, you want to make sure you draw this because if you do, like we saw earlier, nitrogen is actually a triple bond. We then have 3 of these guys. And we also have 2 of NH3, which looks like this. So when we look at what we are breaking, we're going to break a 1 nitrogen-nitrogen triple bond. And we're also going to break 3 hydrogen-hydrogen single bonds. So the 3, the coefficient's important because essentially we have 3 of those that we're going to be breaking. So you do have to take the coefficient into account when you're doing something like this to make sure that you get all the bonds that are happening there. So if I look those up real quick, I got a triple bond and a single bond. Actually, we'll do this guy before we go here. Each of these NH3s is going to break 3 nitrogen-hydrogen bonds, but there's 2 of these guys, right? Which basically means you're not going to break really or make 3 of them. You're going to make 6 of them, right? 3 in each. So that's going to give us times 2 for the coefficient, 6 nitrogen-hydrogen that's going to be made. So again, if you're not sure what it looks like, quickly drawing it will kind of help you get the right bond. So in this case, 1 nitrogen-nitrogen triple, 3 hydrogen singles, and 6 nitrogen-hydrogen single bonds. I can go back to the table to find those numbers. So for my breaking, we're going to do 1 nitrogen-nitrogen triple bond, which is right there, 946. We're also going to do 3 of the hydrogen-hydrogen single bonds, which is 436. And that takes care of all of our breaking. So that's going to be 946 plus 3 times 436. Gets us 2254 on our breakage. And in terms of our making, as we talked about there on the picture, there's really 6 nitrogen-hydrogen bonds that are going to be made. And nitrogen-hydrogen is right there. That is 389 each, it looks like. So that is going to be 6 times 389. And that will be 6 times 389. Gets us 2334 And this is going to be negative because we are making them. So our delta H for this guy would be 2254 plus negative 2334. And when it's all said and done, based on bond energy, looks like we end up with minus 80 in this case, if I did my math right. Which again would tell us that overall, based on bond energy, this reaction is exothermic. Question on how to calculate bond energy or figure out if it's exothermic, endothermic. And again, probably you do want to quickly sketch. You don't have to do all the dots, but at least sketch it enough that you could figure out if it's a double bond, single bond, or triple bond if you're not sure. And also you do need to, as you see in this last example, take into account the coefficient as well so you don't miss out any bonds. Any questions on that there? All right, we will stop there. We're almost done with this chapter, I think. So we'll stop there. We'll finish up.